Okay, now it is correct. Audio is on. So um, I'll take you through this recap kind of thing. So first we'll discuss about the environment, whatever we are living in, and if we see that everywhere light is there, and because of light we are sensing most of the time, most of the things. Like if you see, if we talk about if we are talking about the day-to-day life, because of light we can see objects, ourselves, other human, and that's how we are sensing them. So same thing, why can't we do with the fiber optics? Fiber optics are there for data communication, but along with that it can be utilized for the sensor application as well. So most of the times if you are talking about the sensors, there will be three things together overlap, and that makes a data science. It's a called a field called data science. First thing the communication, second thing computers, and then sensors. So the communication way, we can say that we are talking in the orally, verbally, or in the like so many things are there in the communication itself, but it's already like what we can say that it's already has been demonstrated in the various types of various way, while the computers also is going advanced and better compared to the previous version, year by year, or we can say that version by version. But the sensors still we are using, sometimes we are using the sensors which is having the traditional way of doing work. Why should not be implemented the different kind of sensors, optical sensors? So actually it's not too much of explored area. If you are talking about the sensors, it can be designed for the particular task or particular instrument. The sensor can be used like that, but most of the engineers, they will be commercialize it for the what we can say that they need to see the cost as well as the performance. If it is not having the high performance and cost is cheap, that sensor also not good. And also if it is having the high performance and cost is also too high, then also it has the problem. Okay, if it is not performing well also, it is having problem. And if it is performing well and cost is very high, and everyone can't afford that. So that's we need to think. Okay, so that's why this optical fiber sensors came into picture. And you can see here the smart grid pictorial, animated pictorial. In this you can see that there is a the centralized distribution center, which distributes which collects the energy, harvests the energy from this way, like thermal plant or wind, or you can say that hydro plants, then solar panel, and it distributes to the different places according to the load. And this is how the total work has been done by the smart grid. But why we can't use the sensor to replicate this? What needs more power and what doesn't require much more power compared to other, or less power, much less power? For household it is required very less power compared to the commercialized buildings. Okay, so those things need to be taken care, and that can be done easily by this kind of optical fiber sensors. And also the fiber sensors can be used, or is being used in so many things. Like in a, you can see this is a aeroplane, and there are so many things are so many sensors are based on the optical fiber sensors. So my voice is clear to you guys? Please confirm once. If it is not, then I can change something. Any noise, any disturbance is there?
No, sir.
Okay, okay.
Clear.
If you are feeling something problem, then you just let me know. Okay, I don't want to go just like that. Just slowly we'll go, but you should understand properly.
Okay.
Okay. So the sensors can be used for so many things, and is being used in a aeroplane for the different kind of um, um, detection. You can see here that temperature and structural integrity monitor and engine control is there, and here inertial navigation is there. So in inertial navigation you can see that there is a optical fiber sensor based gyroscope they are using, and that is way higher accurate compared to the normal gyroscope, which is 10 to the power minus 3 degree per hour. Okay, so you can compare, and after that also you can see here optoelectronic information processing and um, control system. So as you know that the fibers, optical fiber doesn't have any kind of electromagnetic radiation or electromagnetic interference, as we see in the copper wire or whatever wire we are using in a household, that will be having must have the interference with electromagnetic radiation. Here it is not the case. So this is like a, you can say that the optical fiber doesn't affect by the electromagnetic radiation. It's a very safer to communicate throughout the aeroplane in the sky. Then there will be so many other sensors which are being used and going to used. Just a second. Yeah. So yeah, just I discussed as I discussed with you guys that this these sensors can be used for multiple applications. Now I'm moving towards the next one. Okay, so as you know that the optical sensing, why it is very important, why we should implement, and why it is going to be implemented. So optical sensing has the sub wavelength precision. Okay, micrometer wavelength. Even I can say that few nanometer it can be used for the sensing application. Also, it depends on the optical density of the material. Let me check whether it is working. Yeah. So optical density of material like strain and temperature and pressure, which will change the optical density of material, and which can change or fluctuate the sensitivity of the optical um, radiation in that throughout the material. Okay, then it's like this sensing can be non-destructive and non-invasive. Why it is non-destructive? Actually, because most of the materials which can bear the light up to sub-micron wavelength without this damaging or without making any change in the material. Like we can say that for example that optical fiber, the glass fiber we can say, which are going to use, which are being used now. Then just again somebody joined. Okay, so where were we? So I just discussed about this optical sensing, how, like, what are the things like sub wavelength precision we can go, sub micron wavelength precision. Then after that the material sensitive also, then non-destructive technique. And you can see that in this range, this frequency we will use for the more telecom communication, and here it will come like visible range, and that's what, like visible and IR range, near IR, far IR. So that's what we can use for the sensing application. Okay, so moving towards the schematic of the optical source connected with the photodetector using fiber, optical fiber, and having some kind of the sensor which can perturbate the signal. Okay, so here we can say, just a second, yeah. So it can be modulated phase by this. The perturbation can be as either as a phase, frequency, amplitude, or polarization. And how we can modulate this phase, frequency, amplitude, polarization? Due to the change of the strain, temperature, and pressure, rotation, those things. How just now I discussed with you about this, that optical density of material is sensitive to this. These are the parameters, and based on that we can sense what is going to be happen during the perturbation due to this kind of um, um, changes. And also that it's a the problem is with this is the demodulation is the key challenge here. As you know that when we are discussing about the photodetector, the light source is propagating through the light source, the light is coupled into the fiber, and the fiber is propagating the light towards the detector, and it is detected. But there is a one problem actually. If you are using this kind of setup, what will happen is like it will, just a second, yeah. So it will, what it does is like once you are seeing the face from the front side, once the light is falling on your face and you are seeing with the camera, so it's like like you are seeing from the front side, both things are the front side. And another thing is like you are seeing the face, it's not a face anymore, you are seeing the light is coming from the front side on your face, but somebody is seeing you from back side, and it's like the setup says the same way. Once you are seeing the face from the back side, this is the setup. It's like you are staying here and you are detecting here, so light source is coming like this. This is not the best way to detect a signal, sensing signal, which is very weak compared to whatever the light source is propagating. Light source is coupling to the fiber and propagating towards the photodetector. So what should we do for the best sensor, or the to have a best sensor efficiency? We can connect the sensor photodetector towards the optical source itself, and both the light is propagating this way, radiation is propagating, and perturbation is happening. And once perturbation is happening, either it is a phase change, frequency, amplitude, polarization, anything, which will be reflecting a tiny amount of information which will be detected by the photodetector. And you can see this equation that the electromagnetic the electric field of the electromagnetic radiation has been given with this having the different parameters like polarization, this is the amplitude, then frequency, then here phase. So it can be more modulated. The electric field of the electromagnetic radiation can be modulated with these four kind of phenomena. The modulation can be done. Okay, so these are the best example to show how this sensors can be used and is working now. Okay, so why optical sensors? As I discussed previously also, that optical sensors has like very precise, if even if it is a minimal amount of uh, signal is coming to the detector, it can be detected easily compared to the electronics. Also, the electromagnetic interference won't be there in this. Okay, then um, these are the things. Okay, then if you talk about the different kind of detectors, there are sensors like various sensors which can be um, capitalized as amplitude modulated sensors, phase modulated sensors, wavelength modulated sensors, polarization sensors, and distributed fiber sensors. So one by one we'll be talking about the this kind of sensors which having the different modulation. So first we'll go for the amplitude modulated sensors. uh, you can see on the screen that how the gesture recognition and what we usually do once when we are taking selfie on camera and we are showing our hand, our palm, and is clicking the picture, that is a gesture recognition. And this is the best example of the amplitude modulated sensors. So where that the camera sees that your palm is being detected by the using the array of light pointed projected towards the camera, and based on that the camera or the mobile, it um, works to like process that and clicks the picture. The same way, this is how the IRCCD detects the points, and based on that the gesture recognition has done. And this is like a amplitude, like point by point it reads, and that's how the amplitude modulation sensors works. If you talk about the phase modulated sensors, guys, if you have any doubts in the middle of the session, you can ask. Okay, I don't know, all muted. I don't know why all muted as well. Yeah, you can unmute it. Okay, no issues. I was thinking like I muted you. Okay.
Sir, I can unmute.
Okay. No issues. So we are going towards the phase modulated sensors, where we are using the Mach-Zehnder configuration. And why Mach-Zehnder configuration you use or important for the phase modulated sensor is whenever the wave passing through the measurement through one arm is delayed by the another one, and that's how we can have too much differentiate compared to the reference and the measurement path. And that's how the phase can be modulated, and that's how we can detect the signal. Once the incoming signal is coming from this way and split it into two, I1 intensity and another intensity, and then both are merged here, and it can be seen with this equation, you can see. Okay, and then the phase is given here with the equation that 2 pi n effective L by lambda. So here that the phase change is directly proportional to the refractive index of the material and length, or you can say the fiber, optical fiber, we are talking about the optical fiber. And small change in the wavelength can also be detected because the length is too high, way high. So it can be an amplitude of 10 to the power 3, 4, 5, 6. So you can understand that how much accurately we can measure the phase modulated informations here. Similarly, the phase modulated sensors can be made by the Sagnac interferometers, where it can be used as a gyroscope. And as I discussed with you that it's already being used in a aeroplane, where this optical fiber based Sagnac interferometer is used with for highly accuracy, like 10 to the power minus 3 degree per hour accuracy is possible. Let me check, somebody's coming. Yeah. And the clockwise and anti-clockwise rotation happens because of the input signal and output signal can be detected, and the with a small uh, with a small rotation in the Sagnac interferometer can also be have very large response to the output. Okay, so this is how the phase modulated sensors works based on the gyroscope, based on the Sagnac interferometer. Now we are discussing about the polarimetric sensors, where you can see that the polarizability is, just a second, yeah, sorry for that. So the polarity, the E, and here it is like a magnetic flux density, and here that magnetogyration coefficient. Once we are seeing that the change in the theta value here is directly proportional to the B and gamma. Okay, both you can see here, and length as well. But once if we are seeing that the change in the theta, it will change the polarity of the um, uh, electromagnetic radiation or light signal. So once we are coming back to the, like, if we are giving from the another side the light, and the reflected light will be 2 theta, double of the it's like a double of the theta of that whatever is given from the backward side. So rotational angle is inversely proportional to wavelength, as we know here, and that's how this polarimetric sensor works, and it is already being used in so many places. Okay, then we'll talk about the fiber optic sensors, fiber optic current sensors. Here what is happening is, like, the light source is connected with the fiber, optical fiber, and polarizer is there, then sensing coil is there, and sensing coil senses the inductive current. Actually this should be like this. This is a polarization beam splitter, and the vertical polarization will go to this optical receiver, and horizontal polarized light will move towards the optical receiver too, because of this polarization beam splitter. Okay, so this is working as an analyzer here, and this can be used for so many applications, because the tiny amount of current, it's being used in a this just a second, somebody joined. It's being used in electric stations, so there the tiny amount of current can be measured, like 0.1 ampere current as well can be measured to few kilo amperes current also with the linear sensing. Linear sensing in the sense either it will be 0 or 1, either it is leaking or not leaking, that can be sensed very precisely with the that much tiny current with a very high also. Okay, so this is the example of the best example of the optical fiber sensors. Then if you talk about the whatever we have talked till now, the polarization, amplitude and phase we have discussed already, but we have not discussed about the wavelength modulation. That is very rugged, we can say, modulation in terms of the fiber optical sensor. Why it is rugged? Because the amplitude, the phase, the polarity can be tuned, can be changed with the slight perturbation of the like a strain, temperature, perturbation, pressure or rotation, or any external issues also. If you are stretching the fiber, it can be also it can make somewhere here the it can change the amplitude, intensity can be decreased. So amplitude and those things are it's, it's good, but wavelength modulated sensors are quite rugged. So you can use it very you can say that it's more advanced than them, because it can be sensed very easily, and also it doesn't require so much of the tuning for the sensing. Okay, so as you can see, there's wavelength modulated sensors, how it works actually. So if you have a fiber optic sensor, optical fiber, in this is the cladding part, you can see, and this is the cladding part, and this is the core, and there are like phase changing material. You can see here few places phase has been changed, and based on that the light which is propagating from this way towards this will have some kind of absence of wavelength, because the light is the light is also reflecting back, few wavelength of light is reflecting back because of this phase modulation. And it can be easily understand with the phase modulation. Okay, the wavelength modulated sensors can be worked with easily with the phase modulation. And how we can change the phase? Phase can be changed with the temperature, again the same thing, but the amplitude in polarity and the what was that? Yes, polarization and phase can be it's very difficult to analyze if you are using very slight variation for the sensing application. Okay, so there this wavelength modulated sensors can be used, which has the low insertion. Why we are using this Bragg's grating? This is like a grating. Okay, so why we are using this grating is like because narrowband filter with sharp roll off, low insertion loss, no mechanical alignment, it's very rugged, and no electromagnetic interference. So that's why this is best to use the Bragg grating, fiber Bragg grating, for this wavelength modulated sensors. Okay, if you see here how the perturbation for the different wavelength is being or different application in the same sensor shown here, like wavelength here lambda 1, it works on the lambda 1, it works on the lambda 2, and that shifts along with the perturbation. Okay, and that can be sense in a backscatter mode, not in the transmission mode. So this is how the wavelength modulated sensors works. Okay, and it can be, here it's mentioned already, that could be strain, temperature, pressure, magnetic field, spectral shift correspond to the magnitude of perturbation. Okay, so it can shift from lambda a to lambda b, either it is lambda 1 to lambda 5. So based on the situation, which sensor is working, like which perturbation is having the most significant uh, response. Okay, so till now we have discussed about the amplitude, phase, wavelength and polarization. We'll discuss about the distributed fiber sensors. uh, just give me 5 minutes, I'll just come back and we'll continue it. Okay, then we'll go for the question answer sessions. If you have any doubts for this week questions, let me know.
Okay, sir.
Okay, Yeah. So um, moving towards the next type of sensor, that is distributed fiber sensor, which generally senses the Raman and Boolon scattering based on like based on the choice. Um, so as you know that like we have discussed all the parameters like for sensing based on the optical parameters, amplitude, phase, frequency, and um, polarization. Now we are moving towards the different thing which can be used for the like quite harsh condition sensing, like breeze or dam or aeroplane, to sense or to measure the structural integrity, like how much it is stable, and structural health monitoring system, then parameter sensing, then time intervention can actually. The problem is the with the sensing, this kind of sensing, it requires that human intervenes, and based on that it will be so much costly. If you are making a bridge and you want to sustain it for 50 years, and you need to be having an inspection year by year or quarterly, if it is a very sensitive area, if it is in very sensitive area. So the construction cost and the maintenance cost will be more compared to the construction cost if you are implementing this inspection as well. So that can be easily monitored with this distributed sensing. What does it mean by distributed sensing? It has different kind of sensors, or it has the sensor which can detect the different parameters of the particular application. Suppose here we are talking about the downhole monitoring in oil or gas exploration. You can see here that how the temperature we can monitor based on the depth. So if something is moving back like downhole, it can be having the different temperature gradient actually, so which can be detected easily using this kind of sensor, which can directly um, just a second, yeah, which can directly uh, response the material, which can directly response to the temperature, and based on that the change will happen in during the sensing in the fiber, and that can be detected again back in the reflectance backscatter mode. Okay, reflectance mode. So again, the leak detection, power transmission and distribution, that I have discussed already with you. Fire detection, fire again, temperature, place, then environmental geothermal, like pressure, everything, it will be included. So so you can see here that some kind of plot is there. In this, if it is having the um, each and every peak says about the um, various parameter for that particular, either it is particular detection. Okay, so if you think about the distributed sensing using the fiber like FBGs, then what will happen, like there will be two types of distribution sensing. One is quasi. Why quasi we are talking about? Because it will be having the distance versus strain. Like suppose you will be having the strain here, so you will get the change in the wavelength particular this place. Okay, so you can detect it. If you have here, it can be this one. Then the strain is various position, you can detect. But what about if you want to detect in the middle of this place, this area, this area? Okay, So that is the one can't be done by this quasi distributed sensing. Quasi distributed sensing is okay, good, but we need to have the detection throughout the fiber everywhere, and that can be detected by this true distributed fiber sensor. What it does is, this is the same thing, but backscatter signal also, like whatever we discussed about the strain, okay, it's like strain is proportional to the backscatter signal, how much it's coming and what is the coming signal, but we have changed the um, parameter with distance with time. So the uh, optical source propagates the light through the fiber of generated optical source light, and it will be different places. Okay, let me make properly. Suppose it is here now, okay, in the fiber, and suppose it is here now, okay. So you can detect temporarily the backscatter signal, which for that with the receiver should be way faster than the receiver response should be way faster than the normal conventional PIN, okay. So for that we need to use avalanche photodiode and all other things which can gain more signal, and also the speed, maybe it can be used. So here we are not localized area, we are not doing the sensing, we are doing everywhere, okay. The perturbation, suppose here it is happening, so we'll get the information that this particular place, instead of the distance we'll get the time, okay. So this is a true distributed fiber sensors. And if you talk about these things, we need to talk about the distribution is based on the Rayleigh and Brillouin scattering. So Rayleigh is not nothing but the elastic scattering, and the Brillouin also, it's an inelastic scattering, but almost similar to the Rayleigh, okay. So the magnitude of its like order is almost 4 to 5 time of the incident light, transmitted light, okay. And this is also almost similar, but inelastic Raman scattering will be almost 6 to 7 orders lower than the incident angle, incident level. So you can see that when once the light is propagating to the medium, suppose a glass, it will generate so many things. It will also absorb, it will reflect, it will propagate, so many things happens, and during that this kind of during the light matter interaction, these all things will happen. Raman anti-Stokes, Raman Stokes, Brillouins, Rayleigh, okay. And that's how we are detecting the distributed fiber sensor, it's working, okay, based on this. Also this OTDR, optical time domain reflectometry, works. In this also same setup is there. Laser, detector, both are connected to one side in the backscatter mode, and the thing is like here, once the transmitted pulse having some kind of width, larger width, you will get the signal response larger in larger area. So this is what it shows here in this particular image, okay. If you have pulse width smaller, then smaller this one, then you will get the smaller intensity, so detection will be less like sensitive, more sensitive. So this is the full setup of that, where laser generates the signal, coupler towards the through the coupler it goes towards this particular testing fiber, where there will be first obstacle, it will generate the Brillouin scattering, then it will be having some dip, again there will be dip because of splice, then bending loss also will be there, then again this is the reflection. Actually these are the connection in this two, in the fiber there will be a gap, Because of the reflection, the intensity is high, and once it is propagating again, then the um, um, Brilliance scattering happens. And similarly here, reflection, because of the intensity again increases, then it goes to the intensity decreases. So that's how the photodiode is in the loop, connected with the loop of to the laser driver, everything, and based on that it sends the signal. Okay. And here you can see that power in fiber and backscatter power is almost like a uh, decreasing with the distance, but once it is reaches to the PD, it will not be having the, no longer we can detect the scattered power. Okay, so it should be having the detection limit, or it is having the detection limits also. So yeah, so we have already discussed for this week whatever has been, like recap the week, throughout the week whatever the classes has been done for you by professor. Now if you have doubt, you can ask me for this week. For next week we will be having the next session in on Saturday. So let me know if you have any doubts or any doubts regarding whatever I have discussed now. Hmm? Are you able to follow it? Did you saw the lecture? Did you see the lecture?
Yes, sir.
Yeah. So if you have any doubts, you just please ask me. Anything you can ask. It's not an issue if you are having some small doubt or big doubt. If it is too big or too difficult to answer, I can convey to the professor. He will also help you to understand that thing. Or if you are lacking something, maybe if you are not following properly, uh, I can convey to professor. He will also help you with that. So it's not to worry about the content. Okay. Anything?
Sir,
Yeah. Yes.
regarding that fiber grating
Yeah.
between the fiber line,
Uh,
my doubt is
which one you are talking about? Please let me
in
know.
OTDA, Relon OTDA,
Brilliance.
uh, OTDA implementation.
Ah.
We use fiber gratings in between, no, sir.
Yeah. Yeah. Yes.
I don't know if I am imagining rightly.
You. Yeah. What do you want to say actually?
If number of fiber gratings are there, if anything disturbance from the first, it will scatter from that. If it is from the sequence, means it has to go through the first one, second one, and then come back scatter.
I didn't get you. You're like you are talking about the loop is there.
Huh.
Then what is your doubt?
We have to get backscatter signal from the receiver,
Yeah.
which is connected in the observer end only,
Yeah.
the same end. Uh, if there is strain or disturbance in the first fiber grating or perturbation, before true sensor, we
Yeah.
said
Yeah.
that
Yeah. Yes.
different
Yes.
places we
So
keep.
that will be this whole system is in loop. Wait, I'll talk about it. You are talking about this one. This one. So this whole system is in loop now. So if it is having before itself, if you have something here, you are talking about. Am I correct? What you are saying actually? Hello?
Yes, sir. That
Yeah.
is fiber black rating
Yeah, yes.
slide,
Yeah.
slide which is having fiber black rating.
Actually, your question I am not able to understand.
Mhm.
This loop, you are talking about this loop, or which one you are talking about?
In OTDA implementation, we use fiber black rating, no, sir.
Yeah, yes, yes.
Yeah. It will backscatter means it will come to the observer end where
Yeah,
we have detected.
yes. That's what is happening.
Uh, if first perturbation 2 to 3 steps we are having, no, sir. Like
Yes.
if it is in the third step, it has to come back to the first step. If
Yeah.
there is disturbance in the third step and first step, then how will be the signal?
Actually, see, if you have some kind of disturbance also, it can be resolved by this length of fiber by time of flight measurement. So you can measure the multiple times, like that's how we can like calibrate it, or we can have that.
Okay.
Yeah. If okay, I'll note down your question actually. So maybe it can be useful. So you are saying that in the fiber grating, you are talking about this one only, na? Whatever I am showing on the computer.
This one is OTDR.
Yeah.
Next slide after this.
Which one you are talking about
And
then?
after this slide, sir.
Okay, just a
After
second.
next to this slide.
This one.
Next one. Next one. Where FPG? Yes, sir. FPG. Yes, sir.
This
Here.
one. Okay, okay, okay. Okay, you are talking about this one.
Hmm.
So here, if it is perturbation happening, the different wavelengths are there. Each perturbation, it's a distance dependent. So if it is having the perturbation at the first position here,
Hmm.
so the lambda one will be affected. It either it will go enhanced or it can be decreased, diminished.
Okay.
The second place, the wavelength too will be different. Like you can, I showed you that one. I showed here. You see, this is how the lambda A will be different place, lambda B will be different place. If you have some problem here, there the this is one plot you will get. Along with that, if you are doing the quasi, so you will get the strain versus distance also, or you can say the backscatter signal versus distance.
Hmm.
Yeah. So
Okay.
if you are talking about this one, then what is happening is like the temporally you are converting, like you are checking the temporally. Here also you are checking, then slowly, it's not slowly actually, light is very fast. So second measurement you are doing here, third measurement you are doing here, like that. Understood what I am saying?
Okay, sir.
Yeah, light is very fast, but we can detect it with a femtosecond pulses also we can detect. So those things has been done like slowly, one places segmented part time wise. But here it
Okay.
is like if you have some perturbation here and the signal is changing, then it won't affect these things. Or if it is here, then it won't affect these two.
Hmm.
Yeah. Anything else?
No, sir.
Yeah. Why we don't have- So, you have any doubts on the questions? Did you solve that? Week 1 questions. Have you already finished?
Week one questions try to solve, sir. Practice session.
Yeah.
Week one practice session is there, no, sir.
Yeah.
If possible, let us try to solve.
Yeah. Week 1 you have not solved?
Yes, sir. Week one solve, sir.
Solved.
Yes, sir.
Okay, so you want to go for the practice session. Actually,
Yes.
I have not included here because I was thinking like you are already have finished the practice. Then after that you came for week one. Did you try week one first before you?
Yes.
So what's the problem with
I,
that?
so mostly I try to solve.
Okay, okay. There are four questions in practice session, I think. How many are
Yes.
there?
4 only.
Yeah. Um, I'll do one thing. Actually, I need to incorporate here. So give me some time. Then after that, I'll incorporate. Then we'll discuss about that. Okay. In the
Okay.
PPT. Give me 5 minutes. We're in discussion here. Okay. Are you around?
Yes, sir.
Yeah. So what's the what's the problem you have? Did you solve these things? How much point you got actually? Actually, quite interesting questions here.
It is sir. It is solid.
Yeah. So
Yeah.
yeah. So you can see here that the detail has been given all the details. whatever is required. But if you follow one by one only, you will get to like come to the answer, because most of the questions first answer will be kept in the second um, question solution. So that's how it has to be done. So let me discuss with you. First question is, let me go to my copy. Yeah. So what the question is, the common statement is there. It says that a communication link that is 100 kilometer long has to be interrogated using an OTDR. We should be able to detect two slices as separate slices if they are separated by 2 meter. I have to improve the SNR, and hence I am averaging over 16 traces by sending 16 optical pulses consecutively into the fiber. The wavelength of my laser source is 1550 nanometer. Take R is equal to minus 52 decibel per microsecond at 1550. Take coupler and slice loss C as 2 decibel, fiber loss alpha as 0.25 decibel per kilometer at 1550 nanometer, and N effective of the fiber is 1.5. So let's go with the let's move with the statement for the question 1. Question 1 says that what should be the optical pulse duration TP for the application. So we need to calculate the optical pulse duration. For that we should know that the equation which has to be directly kept, like del z, okay, is equal to c speed of light, TP pulse duration, divided by 2n effective. Okay, so we have all the data, like we have the separation del G here, 2 meter. C you know already, 3 into 10 to the power 8 meter per second. Then TP you need to calculate for this question, and 2 into N effective is 1.5. so that's what you have to do. You need to calculate, then TP will come. Did you try this way? Formula you didn't understood. The separation, the pulse duration and the separation, you know already what is the relation. Like the let's say like duration will be proportional to the separation, how much it's. So that's why this formula is used here. Okay, you need to practice more, I think, with this, because you know already that this is the separation formula. Separation formula says the speed of light into the pulse duration divided by 2n effective. Then yeah, so you need to modify it in such a way that you can get TP. So TP's equation will be del z 2 into del z into n effective divided by C. That's it. If you do this, you will get the answer. So can you calculate this like TP now, whatever I have told you with that? It's quite fast.
Yes.
Just let me know what is the answer for this. We'll move forward for the next one.
2 into 10 power 8. So 20 nanoseconds.
10 to the power 8 actually, whatever is mentioned.
10 to the power 8.
Speed of light 3 into 10 to the power 8 meter per second. So it's a 2 to the power 8, yes, whatever you are saying. Velocity, so del z is equal to, we can write like this maybe.
20 nanoseconds. Answer.
Z is equal to velocity of light inside the fiber divided by 2. Okay, so moving towards the next question, what is the dynamic range L for of the instrument? So you need to like L of the instrument. What is the dynamic range L of the instrument? So for this also we have one formula. Just I'll let you know. Where is it? So as we know that length is almost 100 kilometer. Link length. Let me change the pen maybe. Color. Okay. Length, I'll write better. 100 kilometer. Did you try to solve this one? You got something? Any value? Okay. So it's mentioned length already, and then alpha value also we have fiber loss, which is 25 0.25 sorry 0.25 decibel per kilometer. So that's what is the dynamic range L for the instrument. Actually it should not be, I don't know whether total loss should be actually, or it is the dynamic range only. Have you tried this one anytime, this question?
No, sir.
Yeah, so I don't think so. Like I don't know whether it's a loss, maybe loss. Let me check this one and I'll let you know. First we'll go for the next question. Then question number 3. I'll tell you within a few minutes. Okay, that question answer.
Okay.
So here already is if a launch a pulse of a peak power 20 decibel meter into the fiber, what is the backscatter power at the detector? As you know that the peak power, if you are using the 20 decibel per meter in fiber, then it will take a 1 to 2 paths, like double of the path. So like just a second, I will discuss. So we have P input, power input, which is 20 decibel per meter. Then we have R, which is minus 52 decibel per microsecond. Okay, at 1550, because we are discussing about the 1550, I am not writing that. Then we have TP also, just now we have calculated. That's why I am telling that all are interlinked. So first question if you solve, then second will automatically come. So it is 20 nanosecond. Now we need to correction. We need to do correction for R. Okay. So first thing we need to do is correction is equal to 10 log 10 0.02 microsecond. Or microsecond, why we are taking, because already it's in microsecond. So 0.02 microsecond. Okay, so TP. So it will come around minus 170, minus 17, sorry, minus 17 decibel. This is correction for R. Then the backscatter power we need to calculate. Have you tried this question first previously, or you were stuck in somewhere?
Yes, sir. I didn't try all this.
Okay. So I'll just tell you what are the ways you need to do. Then you need to go for the backscatter power calculation. Actually, I'm not able to write on the screen. That's why I see so much mistakes. So 20 decibel minus 52 decibel minus 17 decibel, approximately minus 49 decibel meter. Minus decibel meter. Okay, per meter. So this is the backscatter power. Then you need to discuss about the coupling loss. So coupling loss will be, this is backscatter power, when coupling loss will be coupling loss can be calculated like P detector is equal to minus 49 dBm, the backscatter power, minus 2 minus 2 dBm, which is splice loss C. Okay, splice loss. Then 51 again, 51 or 50, yeah, 51, where is it, 49, 52, yeah. Do we have 51? 52 decibel meter. So decibel meter. So this is the photo detector loss. Actually, I made a mistake actually, just a second. So these two, overall it will be 51. That's why it was confusing. 51 decibel meter. Okay. So now you have coupling loss. I'll just remove this part. I think I should. So here's done. Now what we are talking about, we need to convert into watt. So we watt in decibel per decibel meter. So how we can convert? P watt is equal to 10 to the power minus 51 minus 30 divided by 10. So it will come as t to the power minus 88, t to the power 10 to the power minus 8.1, which is approximately how much nanowatt or peak? It means 10 nanowatt. Understood what I did? First, the power input you need to know, then you have that R value, okay, then you have the TP which we have taken from this question 1. Then you need to calculate first correction in the R, so you will get this minus 17 decibel, okay. Then backscatter power, you need to actually add it, this one correction R and this power input. Then coupling loss you need to calculate, so for that also again the the backscatter power and this slice loss you need to incorporate. You will get the photodiode what is that, P8 detector. Then you need to convert into watt, so it will come to 10 nanowatt. Somebody wants to join. Yeah, so understood how I did this one, this question?
Watt conversion formula last.
Which one, the P watt, power watt
Last.
for the watt, or which one?
Yes, sir. Last
Yeah.
step.
Last step is just a second, I will tell you.
हे बघ माझा अभ्यास बघ.
Somebody is talking so much.
हो खेळते.
What did I do? Let me. So this is the. Okay, I can't copy paste here. Huh? Maybe here. Is it visible now? Yeah, this is the equation I used.
Okay, sir.
Understood? This is the equation I used.
Okay.
Yeah. Now where we were, 3 is done, 4th one we are going now. So what should be the time difference between two consecutive pulse, so that the backscatter from the first pulse and second pulse do not overlap each other? So for this also, just I'll remove those things. It's too much crowded here. Okay. So have you tried this one?
No, sir.
Okay, you should try that. Huh? It's easy actually compared to the previous one. As you know that the L, the length, mm, 100 kilometer. Okay, then N effective 1.5, mu is equal to C by N effective. We know all these things. Okay, so N effective 1.5 is there, then mu is equal to 2 into 10 to the power 8. Okay, meter per second. Now the round trip, you know how it will be, like the length will be double because it's a round trip.
Okay.
So 2L divided by mu. What happened suddenly? Something happened. Yeah. So this is the round trip. So the time will be what? Yeah. So for round trip the time will be this one. T is equal to 2L by nu. And L, as you know, that 100 kilometer, and nu already you know those things. So if you keep, you will get the what is that? Should not overlap. So we'll get the exact time difference.
Okay, sir.
Okay.
1 micro. Okay.
Is did you understood what I said? Fine.
Yes, sir.
Yeah. So where we stuck? Actually, question number 2. Actually, that is correct. Whatever we were doing. Let me go to the slide. Here, the dynamic range L depends on the total length. Total length is 100 kilometer into the fiber loss is 0.25 decibel per kilometer. So if you calculate this 100 into 0.25 decibel per kilometer, what will you get? 25 decibel, and that's what the correct answer is. Okay, so dynamic range is calculated with the total length into fiber loss. Understood? Any doubt you have now still?
Yes, sir. Fiber loss 25 already mentioned. 0.25
0.25
mentioned.
0.25
Ah,
kilometer.
mentioned. Yes, sir.
0.25 decibel per kilometer. So
Yes,
if
sir.
you multiply it, then it will be 25 decibel. Okay.
Okay, sir.
So I think, should we stop or you want to continue? Anyone? Any doubt you have? Today's session is first session, so we can take more doubts. Still we have some time, 10 minutes. Somebody will please provide video recording of this session. Yeah, sure. We'll provide the video recording. If you have doubt also, you can ask here. Next week also, on Saturday we'll have some again discussion from 6 to 8. Okay, next Saturday. So you can bring your doubts as many as possible. We can discuss here. Also, I will also learn so many things from you. You will also learn. Okay. I'm not solving these questions because it's an assignment, so you need to complete it. After that, if you have doubts, we can solve one by one. Okay. Anyhow, these questions are very useful for your the final examination if you are giving final examination. Please ask me any doubts you have. Okay, then if you don't have any doubts, then I can conclude today's session. We'll meet on next Saturday then with more doubts and more discussion. Okay?
Okay.
Yeah. Okay. Then.
Thank you, sir.
Yeah.